the idea for calculus, which is called derivative. So back to chapter 16, okay, 16D, what we have done. Well, 16C, we said, what is the average rate of change? I said, not all the relations can be described as a linear. Like for linear, it will be the same at all the gradient will be the same. The rate of increasing or decreasing will be the same at every point. But when the relation is not a linear, like normally it's a curve. So the instantaneous rate of change is represented by the gradient of the tangent at any point. For example, I have a relation like this, and I can say that's a VT graph. That's how my velocity and time change. For example, I want to find at that time, like time equals to 2. I want to know how quick the velocity is changing according to time. So I can draw a tangent at that point. Well, tangent is the linear that only touches that single point for the curve. Then we can find the gradient. Well, I can work out there's only one line, okay, only one such line. Let's say this is y equals to mx plus c. The m of that linear is the instantaneous rate of change at that point. Okay, is the instantaneous rate of change at that point. Therefore, at all different time, like my instantaneous rate of change will be different. Well, for example, at that point here, if I draw a tangent will look like this. Well, it's not, you can see the gradient will be slightly different from the pink one. Well, if I choose a point here, the instantaneous rate of change is really large because this one got a more steep linear. So you got a larger instantaneous rate of change. So what we can see is at different point of this curve, all the instantaneous rate of change will be different. Well, maybe not all. There might be some point have the same gradient, but most of the point will have different instantaneous rate of change. So what we're trying to do by using calculus is we're trying to work out what's the instantaneous rate of change at all of these points. I can say, oh, at t equals to 2, my rate of change is half. At t equals to 1, for example, that's 1, I can say my instantaneous rate of change is 4. So how we can work out that? Recall the idea from chapter 16. Well, we haven't learned, we haven't learned that yet. The derivative, like we don't know what's derivative at that time. So there are two methods we use to find the instantaneous rate of change. Well, the graphical method is I sketch a tangent and I read 2 points from that tangent. And I use that 2 points on the tangent to work out a rough gradient for that linear. That's the first way. And I said it's not that accurate, right? It's not that accurate. The second method is when we know the function, we know like this is y equals to fx. Why I know the function y equals fx? Well, I will get rid of this. Get rid of this. Let's just focus on the point 2. Okay, just focus on the point 2. The method we use at that time is I can choose a point really close to the point 2. Well, for example, it's a point here on the curve, okay, on the fx curve. And then how close? I can choose 2.001. I can choose 2.00001. And I can sub the value, x value, into the function to find the y value. Then I know the x value and know the y value for those 2 points. And I can find the gradient of this black line, right? I can find the gradient of this black line. And also what we know is the smaller the value we add onto 2, the more accurate value I should have for the gradient. Well, I choose the point here. Well, if I can choose an even closer point here and connecting them, that's basically the same line. That's basically the same line. So that's the idea we used at that time to work out the gradient, okay, to work out the instantaneous gradient. And again, it's not that accurate, but it's more accurate compared to the graphical method. So now let's have a think about that. if I said this is 2, this point I choose is 2 plus h. Okay, I have 2 and 2 plus h. What do you want for the h value? Smaller better, right? I can use a word said approaching. H is approaching. Approaching to what value is better? 0. I want the h value to be as close as I can. Well, 0 will be the best one because it's almost no difference between the second point compared to your first point. Then the smaller the better. You know, when you reduce your h value, you will have a more accurate gradient, approximate gradient, right? So when h is approaching to 0, well, smaller, you want to see the overall gradient you work out is approaching to which value. Then that value will be your real instantaneous rate of change. That's why we learn limit first. Okay, we get the idea of approaching. So what is approaching? You know, I can use h equals to 0.1 to work out the average rate of change between that 2 points. I can use h equals to 0.01 to work out average rate of change, like the black line's gradient. I can use h equals to 0.0001 to work out the gradient. So I can observe the 3 gradient I have, and I reduce the h further, make it 0.00001. I can see a trend. My gradient, the gradient of the black line is increasing or decreasing to which value, okay, to which value. Then this is the idea for limit. When h is approaching to 0, what's the average rate of change, the average gradient of that black line is approaching to? Then the value it approaching to will be my actual rate of instantaneous rate of change. Okay, so that's why we learn limit first. If you can see this, okay, this m, the instantaneous rate of change or function f, we use f dash 2 to represent that. So fx is the function. The dash means it is the derivative. It is talk about the gradient at point 2. So we put a dash on top of f. That means is the instantaneous rate of change at x equals to 2. So we have fx. We find f dash x. And we sub the point 2 in. This notation represents the instantaneous rate of change at x equals to 2. Okay, this value should be the instantaneous rate of change at x equals to 2. It is also the gradient of that pink line. Okay, it is also the gradient of that pink line. Why? Because the pink line is the tangent of at x equals to 2, then the gradient of that tangent is the instantaneous rate of change. So they are equivalent. Okay, they are equivalent. So the notation is f dash 2. It is the gradient of the linear, like of the tangent at that point 2. So if we look at this notation here, let's try to interpret what this equation means. Okay, this is an important notation. Let's interpret what that means. First of all, without looking at anything, just look at this pink notation here. I'm trying to investigate x equals to a. Okay, I'm trying to find the gradient at x equals to a. So this is the f dash a means the gradient at x equals to a. Now, what we're trying to look at is, what's fa plus h? What's fa plus h? The y value of the second point, okay? The y value of the second point. It's not the point you're trying to investigate, it's the y value, the point move a little bit right or left compared to that point. Okay, is the y value of the second point at x equals to a plus h. So that's the y value. What's fa? Y value of the point you're trying to investigate is the y value at x equals to a. Okay, what's this h? Okay, this h is interesting. I can put a plus h minus a. What's a plus h? the second value, second x value, right? Second point x value. What's A? First x value. So what's this equation actually? Is the gradient is y2 minus y1 over x2 minus x1. Well, at the bottom you can cancel the a and a, so just left with h. So the distance between the 2 points, okay, the change in x value between the 2 points. So this formula is actually y2 minus y1 over x2 minus x1. Okay, the thing in the pink. Now have a think. This is just an average rate of change, right? It's in between 2 points. Find the gradient, and that's the average rate of change first. Now I put this in front. Lim h approaching to 0, because you don't know what is your h yet. Like your h is just something like there. You don't know what is your h. So what do you want for your h? You want your h to be as small as possible. Then when you're trying to reduce the h value, you want to see what's the gradient approaching to. What's this whole function approaching to? Okay, when h reduce from 0.1 to 0.01, 0.001, 0.0001, you want to see what's the gradient, average rate of change, is decreasing to or increasing to, approaching to a value. Then that approaching value will be the gradient at x equals to a. Okay, will be, like, you can think about is the black gradient. The black gradient can change according to the h change, okay, according to h change. Then when reduce, the value is approaching to will be the gradient at the pink line, okay, at the pink line. We're approaching to the pink line. Because h is approaching to 0, then the average rate of change, the gradient, is approaching to the actual tangent gradient. Okay, so that's the idea for a limit. That's how we work out the gradient, instantaneous rate of change at any point. Okay, that's the formula we use to work out the instantaneous rate of change. So let's make it more general. This is only focusing on A, right? A is 1, A is 2, you sub-value in A equals to 3. This formula will satisfy any point on the curve. Or A can be 1, can be 2, can be 3, can be 5. So therefore, I will replace all the A by X. All the A by X. So what you need to do is just put x equals to 1, x equals to 2, x equals to 3. So for the top function, we can only work out 1 point gradient. Okay, what you get here is a value. So what you will work out is a value. So add x equals to 1, add a equals to 2, add a equals to 3. But the next function, when I change the a to x, for this overall formula here, I can get a rule. F dash x in terms of x. This is a rule. This is no longer a value because a is not a value. You will have x. You will have x left in the function. So overall, you have a rule, not a value. Okay, you have a rule, not a value. Then you can sub x equals to 1, x equals to 2, x equals to 3 in to that rule. Then you will have the instantaneous rate of change at different points. At different points. So this thing is important. It is called first principle. Okay, that is the first principle. First principle is used to find the gradient function, the derivative function for any fx function. Okay. First principle is the most original formula used to find the gradient function or the derivative function for any fx function. Okay, so this is how we can find the gradient at any point, the instantaneous rate of change at any point. So make sure you understand that. Instantaneous rate of change equals to the gradient of the tangent, and that equals to f dash a or f dash x. Anyone mention instantaneous rate of change? Anyone mention gradient at any point, the gradient of the tangent at any point, or remember remind you f dash x? They are all the same. So the notation is f dash x. Okay, so what you need to remember is the first principle. Well, basically the top one and this one is the same thing. Okay, this one and this one, it is the same thing, because one is to find a single point and the other one just change the single point to x to find the general equation. So they are basically the same. Well, before we can really apply this to the question, let's have a think about what's lim h approaching to 0 of 3? Well, I should have a space here. 3 is here. What's lim h approaching to 0 of 3? Remember what we learned yesterday? How we evaluate limit? 3. So lim of any constant will be the constant itself. Okay, what's lim h approaching to 0 of 3x? What's your variable? Well, your variable is lim h approaching to 0. Anything to do with x? No, so what I said yesterday, what that should be? We treat x as a constant. So what we have here? 3x. Okay, we have 3x. What's the next one? Can I stop? Yes? Then after substitution, what I have? 2x squared minus 3x. Okay, sub h equals to 0. 2x squared minus 3x. I only sub h into h. Okay, I'm not going to sub h into x. So that's 2x squared minus 3x. Can I sub? No. Okay, so what I need to do first? So how I can simplify that? Yeah, after factorize, I factorize h. 3x squared plus 4 over h, right? So h and h can get cancelled. So can I sub now? Yeah, but nowhere to sub. So what my answer should be? 3x squared plus 4. Okay, 3x plus 4. Okay, that's just a warm up from yesterday, how we calculate limit. Now we will apply, okay, what I will apply, give you a hint for the next question, is apply the two formulas. Okay, apply the two formulas into question. Okay, we are trying to find derivative. So first of all, this is a function x squared minus 2x. Okay, this is a function x squared minus 2x. Find the gradient of the chord such that P is a point at x equals to 3. Let's find that point. P is the point at x equals to 3. Okay, this point is 3 comma what? 3 comma 3 sub in 9 minus 6, which is 3. So this point is 3 comma 3. This is the point P, okay? That's right, that's the point P. And Q is a point at x equals to 3 plus h. Q is a point at x equals to 3 plus h. Well, I don't know what is h, so I can put any point. Well, I will say h is here. So Q is 3 plus h. What's the y value? Do you know how to calculate the y value? Sub that into the function. So let's sub that in first. we find f3 plus h. Okay, f3 plus h. That is 3 plus h squared minus 2, 3 plus h. Okay, sub the x instead of 3 plus h. So we expand that. That's 9 plus 6h plus h squared minus 6 minus 2h. 9 plus 6h plus h squared minus 6 minus 2h. Well, I have, that's a 3 plus 4h plus what? Plus h squared. Okay, 9 and 6 becomes 3, 6h and 2h becomes 4h, and left with h squared. So that's the y value when x equals to 3 plus h. Well, it depends on what's the h. If h is 0, the y value is 3. If h is 1, then is 3 plus 4 plus 1 is 8. So it depends on what is your h. So I can put this here. What we have is 3 plus 4h plus h squared. Okay, that's the 2 point. That's the 2 point. So what do you want to find? You want to find the gradient of the chord connecting those 2 points. Well, see if we can connect those 2 points. Good. Okay, you see this yellow line here? Okay, so I want to find the gradient of that line. Well, average rate of change. Okay, average rate of change. So the gradient of PQ equals to, well, it should be f3 plus h minus f3, right? The two y values subtract, and it's 3 plus h minus 3 is the 2x value subtract. So that's how you find the gradient, average rate of change. So I know my f3 plus h is 3 plus 4h plus h squared, and I know my y value at x equals to 3 is 3. Then the bottom is divided by h. That's y2, that's y1, x2 minus x1 is h. The 3 and 3 can cancel. What we have is a 4 plus h. Here's a 4 plus h. So it depends on what's the h value. If h is 1, then the gradient between p and q is 5. If h is 2, then the gradient between p and q is 6. Well, it depends on what's the h value. Okay? Find the gradient of the curve at pq when h is 0.1. So that's just 4.1. So sub h in, so h equals to 0.1, then the gradient of pq equals to 4.1. So we haven't talked about any rate of change yet. It's just the average rate of change. It's not instantaneous at all because h is not small enough yet. It's just talk about any 2 points, what's the gradient between any 2 points. Now the next one said, hence find the gradient of the curve at P. Hence, find the gradient of curve at P. Okay, when you read this, the gradient of the curve at P. If I want to change that into mass notation, I don't want words, I want a mass notation. That will be f-3. Okay, so what you're trying to find is f-3. trying to remember what's the formula for f dash a. So we're trying to find a specific point, which is f dash 3. So f dash 3 is limit h approaching to 0, f3 plus h minus f3 over h. Okay, so I haven't done anything, it's just a notation. Okay, it's just an f dash notation. For any function fx, I can work out the gradient by using this formula. Do you know this? What's that? What's that? 4 plus h, right? What we work out, h plus 4, 4 plus h, that's what we work out in question A. You already work out what's f3 plus h minus f3 over h. So that's 4 plus h. So what I have is lim h approaching to 0 of 4 plus h. What that equals to? 4. You sub h equals to 0, then we have 4. So the gradient at x equals to 3 is just 4. We use the limit to work out the instantaneous rate of change, the gradient of the curve at P. Okay, the gradient of the curve at P. Okay, this is the formula used to work a specific point. Okay, specific point, just like any point. Now, I want to use, the next question is to use first principle to find the gradient of x at any point x. Okay, when mention first principle, okay, when you see first principle, those two words, the first thing you write is the formula. So f dash x equals to lim h approaching to 0. Okay, any point plus h minus the y value at any point over h. Well, it's x plus h minus x, which is h. It's x plus h minus x, that's just h. Okay, the increase in x. Okay, remember your fx equals to x squared minus 2x. Well, different fx has different rules. Okay, different fx have different rules. So for this one fx, we have rule x squared minus 2x. After you write the equation, the next step is to substitute into the function, like replace the fx plus h by the actual function. So fx plus h is x plus h squared minus 2x plus h. Okay, I don't want the f, I don't want the general expression, I want the specific expression for this question. So that's my fx plus h. Minus fx, well, my fx is x squared minus 2x over h. I forgot my lim. There's a lim h approaching to 0 as well. Well, question is, can I substitute h equals to 0 now? No, okay, I can't sub. So what I can do here? Simplify, well, more detail, like before we simplify, we expand. Okay, so the next step is always expand. So x squared plus 2hx plus h squared minus 2x minus 2h minus x squared plus 2x. That's the numerator. Give you a hint, okay, give you a hint. When you expand, doesn't matter what function you're trying to do. The hint is, for a numerator, well, after you expand, all the terms without h should be cancelled. Okay, any term without h should be cancelled from something. So you can have a look, x squared and x squared, they can cancel because they don't have h term. The 2x and the 2x, they must be cancelled. They don't have x term. If your expansion got something left with only x, no h on your numerator, which means you get something wrong. Okay, so the term only contain h should be cancelled. Okay, from the fx plus h minus fx. It definitely needs to be cancelled. Otherwise, you did something wrong. Okay, otherwise you did something wrong. So what I have on top is 2hx plus h squared minus 2h. Yeah, that's what I have. So what I'll do is that equals to lim h approaching to 0. Factorize, take h out. I have 2x left for the first one. I have h left for the second one. I have minus 2 for the third one. Just 3 terms left. And then divide by h. And divide by h. So I have 1, 2, and 3. So the h and h can cancel from top and bottom. That's my cancellation. Can I substitute now? Yes. So what's the after substitute? What's the answer? 2x minus 2. So my f dash x, after all this calculation, I have 2x minus 2. That's the gradient function at any point. You can say x equals to 1, x equals to 0.5, x equals to negative 2, any value. Okay, you sub any value in. Next question. Hence find the gradient of the tangent at x equals to 3. Well, we work out the gradient at x equals to 3 already in C, but we want to use, hence is use the answer before, like the previous question. So because f dash x equals to 2x minus 3, so how about f dash 3 equals to? That's 2 times 3 minus 3, f dash 3 equals to 3. Oh, sorry. Why I have 3? That's 4. So you can see that's the same compared to answer C, which means it should be right. Okay, it should be right. So for C, this equation only works for f dash 3. But for D, this equation will work for any value. Okay, will work for any value. So we'll recommend first principle directly and then sub values in. Also asked to find the gradient at x equals to a. So f dash a equals to 2a minus 2. F dash a equals to 2a minus 2. Alright, so the last one asks you find the coordinates. Okay, coordinates means x comma y of the point on the curve at which the gradient of the tangent equals to 0. Okay, gradient of the tangent is f dash x. Okay, gradient of the tangent is f dash x. So what you want is f dash x to be 0. F dash x to be 0. So what I have is 2x minus 2 to be 0. X is 1. Okay, that's the x value. The x at x equals to 1, the gradient is 0. So now I need to work out f1. f1 is 1 squared minus 2 times 1. That gives you negative 1. So at point 1 comma negative 1, I have gradient equals to 0. I have gradient equals to 0. So let's have a look. What is the point 1, negative 1 on the graph? Just want to give you a bit idea on the later on study. X equals to 1 is here. So is this turning point? Can you see 1, negative 1 is this turning point? What's the gradient at this turning point looks like? Like the tangent, the line. What kind of line you have? A horizontal line. Okay, because it's the flat point. So you have a horizontal tangent, like your tangent will look like this. So what's the gradient for horizontal linear? 0. That's why you will solve out 0 at this point. But just want to give you a little bit graphical understanding on that. So because that point is like a turning point, that's why we have a horizontal tangent. It can't be like with some gradient. So the gradient of the horizontal linear is 0. So that's why we solve out f dash equals 0 is that point. Okay. So this entire question shows you both formulas, first principle and the gradient formula for any single point, like point A at 3, for example, for this one, and then we use first principle again to find the actual gradient function. Okay, so gradient function f dash x. So, well, for the rest of 7 minutes, I want you to try example 3 by yourself. But before we do that, ask you something. When we learned the polynomial chapter, what's a plus b cubed? What's the expansion for that? A cubed 3a squared b plus b cubed. How about a minus b cubed? Yes? Yep. Minus b cubed. Okay, so for this question, you need to use this formula here. Okay, you need to use that one. So trying to use first principle to find out the f dash x for me. Okay, so I will go through this one with you tomorrow. So you work on this for the next 6 minutes.